For the next session, I would like to invite Professor Pavan Nukala. Quick introduction. He obtained his bachelor's and master's in metallurgical and materials engineering from IIT Madras in 2009, after which he joined University of Pennsylvania for his PhD in material science, and after that he worked for 2 postdoc stints at University of Paris-Saclay and University of Groningen, Netherlands. Professor Nukala's lab currently focuses on correlated oxide, ferroelectric and piezoelectric oxides, and phase change memory for electronics. So, without any waste of time, I would like to invite Professor Nukala for his talk.
Yeah, thank you. Okay, fine. Wonderful. Thank you, Aman. Thank you for the introduction. And so I just want to start by asking how many of you are bachelor students and master students? So my talk is aimed at you. Okay? So the others, if you feel disappointed, I'm sorry, but yeah, so I'll try to make it a bit pedagogical. And so I'll come to the quantum part of what I'm doing later. But first, the premise of the talk is that there are what are called quantum materials that can be used beyond just quantum computing, right? Although I'm going to relate to some of the materials that I'm going to work on, which are also related to the sort of quantum computing that Shankar had shown. But the focus of this talk is going to be on quantum materials, okay? Some of the quantum materials. What is a quantum material is something that I will define in my own way, okay? So a brief introduction to what we are doing in my group. So that's why I asked them to give me some chalks and duster also. I'll go there once in a while. So for example, if you look at this picture, right? So I'm going to look at the rival of quantum computing now, which is called neuromorphic computing, right? So that is the idea is to compute like how your brain does computation, right? So if you look here, right? So this is an image. This is what is called a 2-photon image of calcium ions that are in a sliced cortex of a rat. Okay. So if you see here, so whenever there is that blink, right? So that means a calcium ion is coming in and going out, coming in and going out. And you know that a lot of activity in brain is dependent on your sodium and calcium and all these ions going in, coming out. That's how we are generating these signals, etc. Right? Now, if I just so just take a look from far away, I say that okay, this is very random, right? So the way this is firing and not firing is very random. But it turns out that this is not random. What happens in brain is very sort of correlated noise, right? So all this noise knows about each other, right? So this is correlated noise. One of the activities in my group is we work on materials that actually produce signals like this, right? So on a larger scale, you take a slice of brain, and so in one material platform, can you produce signals like that are present in the brain, these correlated signals, and can you compute with them, right? The sad part is I'm not going to talk about that, okay? So and again, the material platforms that I'll be showing have, some sort of quantum nature in it, right? So on and so forth, but that's not what I'm going to talk about, right? So this is, you take the entire architecture of brain and put it in one material and try to use it as complete neural network, okay? So that's not what we are going to talk about. We are going to talk about something which is here. Now I don't know why this is sort of stretched, but that's okay. Where, so the other way of approaching neuromorphic computing, if I may say, okay, so this is the introduction. Let me go from here. So the essential ingredients of neuromorphic computers are, you have to have elements that behave like neurons, and you have to have elements that behave like synapses, right? Now brain is, so it's about 1 kilogram in weight. It has about 10 power 11 neurons, 10 power 15 synapses. 10 power 15 synapses, right? So if I start making these synapses and neurons with transistors, right? I have to put 10 power 15 transistors in my chip. Now, so even with the current day CMOS technology, you can at the maximum put 100 billion transistors, right? So not 10 power 15 transistors, okay? So this is a technological challenge, and even doing that, so the metabolism that your body provides for functioning of brain is about 20 watts. It's very low power, right? So with low power, you're trying to understand me, you're trying to look at me, etc., right? But actually, people have tried doing that. So they tried building neurons and synapses using these transistors. And if you do that, one neuron can be, so you can do that. It's not that it's impossible. So you have to put some, 30 transistors to build one neuron. A very, very basic neuron, okay? And you have to, so similar number of transistors and capacitors and all these circuits, you have to put them together to build one synapse. And, so this is what I'm showing is called Spinnaker. This is in Manchester. So this is built in Manchester. So this is a very good engineering marvel, if I must say. It emulates the visual cortex of brain. So how you, process image processing, etc., that your visual cortex does. So this emulates quite well. You can give it commands and it will process very parallelly like a brain does, right? But if you look at this still has 10 power 9 neurons. And so it takes 100 kilowatts to power it up, okay? So there is really some problem with power, right? So if you directly want to brute force emulate, what's happening in your visual cortex. And if you want to really scale it up to these numbers, so this person standing here, his name is Steve Ferber. He's the person in charge of building this, right? So the leader of this program. So you would need the head, you would need a head the size of an aircraft hangar. So that will be the footprint. And you need a nuclear power station attached to it, right? And I don't need a nuclear power station to talk to you and do all sort of cognition, right? So it's a difficult problem, right? So if you want to build an architecture like a brain, it's a difficult problem, right? Now this is where material science comes into play. You have these elements called memristors. So now you can use what is called one memristor to emulate one neuron, or one memristor to emulate one synapse. And you can make these sort of architectures like what are called crossbar architectures and try to do some computation here and there in this IoT, etc., right? So you can sense, you can compute on the spot, right? So what is called edge computing. You can do these sort of things. Nowadays, this is what is becoming popular, right? So there are some of these materials which are quantum materials. That is what I'm going to talk about, right? So some of these elements with which you can make a neuron. How do you make a neuron out of a material, right? So you cannot, so you have to use some sort of a material that behaves like a neuron, right? So that's what I'm going to talk about. But to give you a overall overview, so the neural network is nothing like this, right? So the neural network is much more complicated, topologically very, So this is what evolution did, and it has figured out a way of low power computation. And so when will we evolve to such a stage? Do we need other strategies to look at, etc.? Is something so that my group works on. Okay. Okay. So let's not worry too much about this. So like I said, right? So I'll look at certain materials, and these are called quantum materials. These are quantum materials. I'll tell you why they are called quantum materials. To actually look at the which actually fire like brain does, like neurons do, right? So I'm going to actually make elements which are like neurons, right? So using the materials, using quantum mechanical phenomena in these materials. Okay, so now what does it mean that I have to make a neuron, right? So let's try to understand how a neuron works, right? So how a neuron functions. So if this is a neuron and I put a stimulus here, this is an electrode, right? At a relatively lower stimulus, I have nothing, right? So this is just capacitively charging and discharging. Okay, so it's just a capacitor, a leaky capacitor. Okay, I increase the stimulus a bit. All right. So beyond a certain threshold, there is one spike that comes up. This is my action potential of the neuron. Okay, I increase the stimulus even further. I have 3 spikes that are coming up. I increase the stimulus even further. My frequency of the spike generation is increasing. Okay, so this is a basic operation of how neurons work, right? So this principle is what is called principle of frequency coding. I can look at the frequency. So neuron is not generating one spike. It's generating a train of spikes that has some frequency, and this frequency encodes the amount of stimulus that I provide to the neuron, right? So this principle I can use in trying to understand what is the stimulus, what is the input that I've given, right? That is frequency encoding. But if I look at, so these are some of the simple operations of neurons, right? So you can model this using what is called Hodgkin-Huxley models, Hodgkin-Huxley models and so on. But there are certain more complex operations that neuron does. For example, here is a neuron, a bird neuron, that interconnects between the eye, between the vision and the auditory, right? So these are called interneurons, right? How do interneurons fire? I mean, so this is one of the firing patterns of these interneurons. these are not the periodic spikes that I showed you earlier, right? So these are very aperiodic and so on and so forth, okay? Okay, so this is one of the behaviors of neurons, right? So there is a way of, you know, having these aperiodic neurons and trying to also, you know, so how you communicate between two aspects of your functions, you know, so has some sort of aperiodic firing, right? Aperiodic yet very correlated, okay? So that's something that I'll not go into details, but this is the nature of firing, okay? Now the question is, can we emulate all these things in inorganic systems, in systems that I can put on a computer, right? So I can't really take a slice of my brain and put it on a computer, but something that is compatible with silicon, something that can be grown on silicon and can be put on a computer, right? So that sort of a thing. Okay, so all right, so then I need some inspiration, and I will look at inspiration again from biology, right? So what is really neuron doing while it is firing, okay? So I have, you know, so this is, does anyone know what this is? Some people who remember biology, the younger folks. Very good. It's a cell membrane and it's a bilipid membrane, right? I also didn't understand before I started reading it. So very good. So this is a cell membrane. It's this bilipid membrane. So this is the cell membrane of a neuron, right? Now this is you know, a schematic from a pig gut, right? So the neurons in a pig gut, and at around the, you know, the body temperature of a pig gut, right? So this guy has a phase transition. So which means that whatever looks crystalline here, right? So there is this orderly arrangement of all this bilipid membrane. It turns into sort of a jelly phase at around the body temperature of the pig gut, right? Now what people have shown is when a neural spike is propagating, it should propagate through the cell membrane, right? So it is propagating inside the neuron and the axon. You know, it is this phase transition front that is propagating, right? Because it is this, so at around the body temperature, you give a small stimulus, it takes it above the phase transition temperature, it generates a spike, and then the spike starts to propagate, okay? So that's the, you know, some people argue that is the fundamental nature of a neural spike. It is, you know, all these ions are moving in and out, that is there, but that is only happening because the cell membrane, because of its phase transition, is changing its capacitance. If it changes its capacitance, I attract some ions and I remove some ions, right? So ionic motion is sort of a consequence of this phase transition front propagating, okay? Okay, so now if a phase transition, so if I have a phase, you know, if I have ice that is turning into water, now I'm reducing my problem to ice and water, right? So something as complicated as neurons to ice and water, right? If I have ice that has turned to water, what will happen to the volume of ice at 0 degrees when it converts to water? Sorry? Increases or decreases? Increases. Okay, ice to water, ice is a high volume phase. That's the only, you know, exception. Typically solid to liquid, you have an increase of volume or decrease in density, but ice to water is the exception, right? So ice has some properties, okay? So at phase transition, I have properties such as volume, enthalpy, area, all these things are suddenly changing, right? So now I'm saying that a neuron is nothing but it's a propagation of this phase transition front, right? That is electrically active because one phase has a different electrical property than the other phase, right? So I have an electrical spike that is propagating. But since it's a phase transition front, there is a volume wave that is also propagating, some density wave that is also propagating. What are these density waves called? Compressions, rarefractions, sound waves, right? So essentially this is also a sound wave. It's not just an electrical wave that is propagating, right? So your neural signals are electromechanical in nature. They are not just electrical, okay? So they're electromechanical in nature. And the fundamental reason comes because there is a phase transition, underlying phase transition, okay? And you know, so these guys have actually shown that this is a sound wave during the spike, right? So they also measure the displacement of this neuron and there is this displacement wave going on. Okay, now what is the material that we can use to get to here, okay? So now I want a material that can transition its phase, okay? I indeed have such materials. So one of them is called vanadium dioxide. Vanadium dioxide actually transitions upon heating to beyond about 65 to 70 degrees Celsius. It transitions from an insulating phase to a metallic phase. Okay. So why is this insulating? Because insulators or semiconductors, they reduce their resistance while I'm heating, right? So in fact, the resistance of this is much higher than the resistance of this. There is some 2 orders of magnitude change in resistance, right? So it transitions between an insulating and a metallic phase. So that's what happens in this material. Why does it happen? I mean, so I was always saying that, oh, there is some quantum nature to this. Why does this happen? Okay. So let's use the board for a couple of minutes and then try to see why this happens. Okay. So typically, right? So so let me take okay. So do you know? Okay. So let me just go here. Do you know how? So let's say I put 2 hydrogen atoms. Okay. So this is the 1s orbital of one hydrogen atom, and this is the 1s orbital of another hydrogen atom. I bring them close enough to each other such that it becomes a hydrogen molecule. How many states am I making? Oh, I'm not yet using the board, but thank you. How many states am I making? So there is 1 state that comes from here and 1 state that comes from here. You can turn off the light, it's fine. There is 1 state that comes from here and 1 state that comes from here. So how many states am I making? I'm making 2 states. And these 2 states are not degenerate anymore, right? So because the hydrogen atoms are at a bonding distance with respect to each other, I create what is called a bonding state and an anti-bonding state. So instead of bringing 2 hydrogen atoms together, I bring 6.023 times 10 power 23 sodium atoms together, right? So that's a large number of atoms, right? So now I want to make a solid sodium or solid hydrogen, right? Then what am I doing? I'm actually making all these states. Sodium has 1s orbitals, sodium has 2s orbitals, but once they come within sniffing distance of each other, all these 2s orbitals start splitting, right? So into 6.023 times 10 power 23 states. All the 2p orbitals start splitting into the same number of states. All the 3s orbitals start splitting, right? And so on and so forth. Now, 2 sodiums see each other, they are within the bonding distance of each other, means that, the 3s of, so which orbital of sodium sees the other sodium first? The outermost is a 3s orbital of sodium, right? So that's why 3s start splitting even much earlier than the 2p, than the 2s and so on and so forth, right? Now at the equilibrium distance, right, so which is determined by what is called Lennard-Jones potential, let's not worry too much about it. At the equilibrium distance, this is what will happen to be the band structure of sodium, right? So I have this 1s state, which is what is called a core level. I have 2s state, which is also called a core level. I have such, n such 2s states, but all of them are degenerate. If I put an electron in the 2s state, that electron knows which sodium it belongs to, right? So it is quite localized electron. I have 2p states, which are sort of delocalized. This is called the valence band of sodium. And I have the 3s states, which are, which is what is called the conduction band of sodium, okay? Now, I have n electrons, let's say, in n states of sodium, right? So if I have n electrons in n states of sodium, there are n states here. So how many of these states will be filled? I have n electrons. Each sodium is giving me 1 electron, each, right? So 1 3s electron, right? There are n such 3s states. So how many such states will be filled? N by 2, right? So it is half filled, right? So if it is half filled, because every state can be filled by 2 electrons, right? So our man Pauli said it at some point. So if it is half filled, what do I have? I have a band which is half filled. So what is sodium? Sodium is a half filled band. What is it? Is it a metal? Is it an insulator? It's metal, right? So sodium becomes a metal. This is the simple band theory, okay? If I take titanium oxide, for example, right? So titanium oxide is my other example. The electronic configuration of titanium oxide is 1s2, 2s2, 2p6, 3s2, 3p6, 3d0, okay? So this is titanium 4+. So I've already removed a couple of electrons, 3d2 and 4s2. I have removed those 2 electrons and I made it 3d0. So similarly, I can make bands for titanium oxide, and I can say there's a 3p band, which is the valence band, and there's a 3d band, which is the conduction band, and there's a band gap between them. 3d is completely unfilled, 3p is completely filled. So titanium oxide becomes a insulator, right? So there is a Fermi level is in the band gap, okay? So it's a simple way of understanding band structure. So bonding and banding on band structure, these are one and the same, right? So the chemists speak about bonding, the engineers or the electronics people speak about band structures. but it's essentially one and the same. So it's how these orbitals are overlapping and what sort of energies are coming up. Okay? Okay, so this is what is called a band insulator, right? Now let us go to our material. So instead of titanium, I put vanadium. Okay? Vanadium has, if titanium has an atomic number of 21, vanadium has an atomic number of 22 or something like that, right? So if I make vanadium 4 plus in VO2, vanadium I should have 1s2, 2s2, 2p6, 3s2, 3p6, but there is a 3d1 that is coming up. Okay? So there is that one extra electron, and this one extra electron should ideally go into the 3d band, correct? If it goes into the 3d band, what happens to vanadium dioxide? Is it metal or is it insulating? It should be metallic, right? It should be metallic. That's what my conventional classical theories tell me, correct? If it is metallic, there is nothing special about this, right? But I'm saying this is a quantum material, right? So something else is happening. So this is actually not metallic. Metallic meaning, no, as a physicist, I always talk about everything at 0 Kelvin, right? So at 0 Kelvin, this is not metallic. At 0 Kelvin, what happens now in vanadium dioxide is, if I put 2 electrons in the same state, that's what you said, right? So every state I'll just give it 2 electrons using Pauli's exclusion principle. If I put 2 electrons in the same state, what will these 2 electrons do? 2 electrons, I put them very close to each other, what will happen? In the same state. Same state means spatially and, k-space wise, every possible way they are there together. They will repel, right? So on the same site, if I put 2 electrons, let's say, they'll start repelling. On the same 1s orbital, on the same s orbital, if I put 2 electrons, they'll start repelling each other, right? In case of silicon, in case of all these classical materials, right, which I don't call quantum materials for a reason, right? I mean, they are quantum, they may have applications in quantum technology, but that doesn't mean that they are quantum materials, right? But, so if I put if I put 2 electrons in the same state, I am okay because the other electrons are trying to screen the repulsion between these 2 electrons, right? So there is some screening that is happening. But in these materials, the screening is very small, right? So all these other electrons, all these other d electrons are not going to screen the field between these 2 electrons that are on the same site, right? So these 2 electrons are like fighting with respect to each other, right? So these are like 2 brothers which are fighting in a family, okay? So then the easiest thing is to separate them, right? Okay, you stay in that room and I stay in this room, right? So that sort of a thing. So what happens then is vanadium dioxide, this state is not a stable state. There is so much of electron-electron repulsion that this metallic state is not a stable state. So what happens in vanadium dioxide, again, so sorry for my handwriting here, maybe I can do the same thing on board, but that's okay. So what is supposed to be like this with a half filled or some sort of partially filled d orbital now splits up into an empty band and a completely filled band, right? So now so this is the, so an empty band and a completely filled band. Now in the process, what did I do? I put both the brothers in this small band, that's okay, but this small, this lower band, that's okay, but this lower band is now under the influence of a nucleus. So this lower band is under the influence of a father who says, I'll beat you up if you, if you fight with each other, right? So these 2 are repelling, but they are under the attractive influence of the nucleus. They are coming more close to the nucleus, right? So that's how this gets its stability, right? So I have 2 bands now. Now you can switch on the light. So what was supposed to be like this now splits up into 2 different bands, right? And this is all happening because of electron-electron repulsions, or so this is hence called a correlated material, right? So there is a lot of electron-electron interactions that are happening that you otherwise don't consider in classical materials. Okay, so that's, you have other phenomena that also comes because of electron-electron correlations. Magnetism, for example, arises out of this, right? So a lot of other, interesting quantum mechanical phenomena come from these correlated materials. I think Bhagwati will speak something about this in the next talk. But here, let me just keep it very simple. There is a split of bands because of this electron-electron fighting with each other. And because of the split of these bands, now this becomes an insulator. An insulator with a band gap of about 0.6 eV or 0.7 eV, I think. Okay, so all right. Okay, so now I'm in this stage, right? So where I have made an insulator. It's supposed to be a metal from my band theory, but my band theory doesn't work. So it is an insulator, right? So because of this, I have to consider electron-electron repulsions in these sort of materials now. So it becomes, so in that sense, it becomes an electron-electron correlated material or a quantum material, okay? So I have my band gap to be about 0.7 electron volts, and if this is my band gap, what will happen if I increase the temperature now? From 0 Kelvin, I am coming up in temperature. Yeah, so, okay, so here, for example, you can also see that the total energy of all the electrons I have to fill up from the ground state all the way up to this state, right? So the total energy, electronic energy is higher than it is here, right? So here, this has moved down a bit closer to the nucleus, right? So the energy of this, and all these are unfilled, right? So the energy of this is slightly lower than the energy of this. So there is some energetic stabilization if my material becomes from this to this, correct? Now I start increasing temperature. If I start increasing temperature, I put more carriers in the conduction band, right? So I'm actually increasing the higher energy carriers, right? This is like a bad uncle coming and saying to one of the brothers, come on, let's go smoke or something like that, right? So this is the influence of temperature, is the influence of a bad uncle, right? So after a while, right, so the energy of this system becomes so large, and these are uncontrollable electrons, they are fighting with each other, right? So they are not in the influence of nucleus, right? So after a while, this state becomes, after a certain temperature or certain amount of carrier density that you put here, this state becomes unstable and it will convert back into this state, right? So that is my insulator. If I change the temperature, at some temperature, the carrier density is enough that it says enough is enough, right? So now I would rather be a metal. I would not be an insulator anymore because there is no specific advantage of being an insulator anymore, right? So I would convert into a metal, right? So there I have an insulator to metal transition. Again, if I change the temperature, if I cool it down, it goes back to an insulator. That's how I have created a phase transition, just out of electrons, fighting with each other and trying to control it in some way, okay? Okay, so you can switch off the light. Thank you. Okay, so that's this phase transition essentially. So until here, it says, okay, now enough is enough. I have been an insulator enough, but there are so many electrons still in the conduction band that, so I cannot take it anymore. So I would rather become a metal, right? So it comes back to being a metal, okay? So this is the metallic state, this is the insulating state, right? So it's a very naive way of putting what is called Mott-Hubbard theory, right? So I have simplified it to a proportion that, so no, the physicists will hate me for that. But, so this is the, so this is the more or less the principle of how a Mott transition happens. This is called a Mott transition, a metal to, insulator to metal transition. All right. So now what do we do? So we grow such materials. In fact, we grow single crystals of such materials using a technique called pulsed laser deposition. Okay, so I will not go into details of the technique unless there are questions. And you can see that, so what I'm showing you here are all atoms, okay, atomic columns of the materials that I'm growing. Here I'm growing something called neodymium nickelate, which is also a Mott insulator. It doesn't matter. Here I'm growing what is called vanadium dioxide, right? So vanadium dioxide also, all you see are atomic columns of vanadium. It is in the phase that I want it to be, etc., right? So, but this is a single crystal of vanadium dioxide, okay? Okay, so the experiments that I do here are what are called transmission electron microscopy experiments. Now, so we do a lot of material characterization, and indeed, so just keep this in mind. It's a detail that you don't need to pay much attention to. In vanadium dioxide, the first 10 nanometers of vanadium dioxide is not really V4 plus. It is some V3, 4 minus delta or whatever it is, right? So this will have a different phase transition temperature than this, okay? So, but that happens in my group, in our growth, right? It may not be general, but just keep that in mind. And that's why you have, although I say that there should be one transition, it looks like there are two transitions here. One for one layer and the other for another layer, right? So there are two different transitions, slightly separated from each other, because the surface layer, when you grow these materials, you have to be very careful about what the surface layer is. If the surface layer is slightly different than the bulk layer, then these sort of effects come up, okay? But we are going to use them for our advantage, okay? So now, if I take a material like this, a Mott material, I make a simple device, right? So this is a 2-terminal device, right? So with a very small channel in between them, less than I think a micron channel or whatever. And, so then I apply voltage, right? I apply voltage Initially it is going like this, the current is increasing, suddenly it goes up, right? Then I don't want the current to overshoot beyond a certain limit. I put what is called compliance, because if the current overshoots, then my device will burn, right? So current burns devices. And then, I reduce the voltage, it comes back like this. So what is happening here? So this looks like it is insulator because it has lower current. Suddenly it switches to something which is metallic, right? But it is happening when I am applying voltage. All this while I said it should happen when I apply temperature, right? So what is happening here? Anyone? No, not that complicated. Simple, temperature keeps increasing, right? So if I increase the voltage, current is increasing, so temperature of the device is increasing, and at some point temperature of the device reaches that 70 degrees mark, and then there is a phase transition, right? So it's a simple Joule heating based phenomenon, right? Okay, so that's fine. So then when I cool it down, right? So there is always some hysteresis because the heating changes phase transition at a slightly higher temperature. The cooling changes the phase at a slightly lower temperature. This is the hysteresis of phase transitions, what are called first order phase transitions. Okay. So there is a hysteresis, so it cools down, so once it cools down to something like 65, it comes down. Okay. Now, if I do the same thing using, so here I am controlling voltage and measuring current, right? Now, it is not the same as if I apply current and measure voltage, because let's say at this voltage, at a voltage of 2 volts, I have 2 solutions for this problem, right? So this material can take either this phase or this phase at that voltage, right? Now, depends on the history, what phase it takes, whether I start here or I start there, okay? But it has 2 stable solutions. But if I'm controlling current, let's say, right? If I'm controlling current, a third solution comes up. So the intermediate solution is not taken, right? So when I'm controlling voltage, right? So because that's an unstable solution, right? But if I'm controlling current, there is no way but for the device to be there, right? So the device is going to be insulating. Suddenly it switches to a metallic state. If it switches to a metallic state, there is what is called a snapback, which means the resistance now suddenly decreases. So the voltage across the device now decreases, right? So if I'm increasing the current, the voltage should decrease. So there is this snapback, and the material goes like this. So there is this sort of an S-shaped curve that you will see if I further increase the current, right? Now this region, right? What is the resistance? What is the resistance of the device in this region when I'm controlling current? Is it positive or is it negative? Huh? Negative. You're sure, or you're just saying because that's fancy? This is correct, right? So if I'm increasing current, voltage is decreasing. So I have a negative, what is called differential resistance, not really resistance, but differential resistance, right? Now, materials don't like to be in negative differential, or some of the electronic, I don't know, how many of you come from an electronics engineering background? Yes. So if I have an NDR, what can I make out of NDRs? They didn't teach you? No. Okay. So you can make oscillators, right? So that's exactly what we are going to do here. So you have a negative differential resistance region here, which means if I try to fix my device there, right? The device does not want to be there. That's the point. That's a fixed point, what is called a fixed point. But the device doesn't want to be there. It will start oscillating between these 2 states, right? So that's what I'm going to do. Okay. So I have this sort of a circuit. I can stabilize the device at all these different points using what is called load line, right? And all right, so let's first show you the results. Maybe I removed it. Yes. So if I apply a small voltage, it's just capacitively charging and discharging. Slightly larger voltage, again capacitively charging and discharging, and so on and so forth. Beyond a threshold, I'm applying about 8 volts. It's not just charging and discharging. I have this oscillations that are happening. Okay. So now what is happening during the oscillations? During the oscillations, what is happening is if I follow both voltage, current and temperature, these are actually physical simulations of the device that we have. Okay, let it come back and I'll tell you again. That's a slow process, so we have to wait. Now at around this, so this is coming back from the phase transition, right? So this is a metal, and here about 70 degrees, it's going to, so the temperature axis follow that, about 70 degrees there is going to be a sudden snapback, right? Yes. So that's my other phase transition from metal to insulator, and then slowly again, so the voltage is increasing. So okay, so let's start from here. Voltage is increasing, current is slightly increasing, temperature is also increasing, right? But all these are very slight linear region. all of a sudden it becomes a bit non-linear, right? So the current is increasing, temperature is even more increasing, right? So these are all related to each other. Time up, okay. And suddenly this goes up and comes down, right? So using so this is how I can generate these sort of voltage pulses, spikes, okay. Now I do that, and so in let's say a device with two different phase transitions. I said that vanadium dioxide has two different phase transitions, right? In a device with two different phase transitions, I can actually create all these spikes which are periodic, which are aperiodic, right? So now I have a device that is behaving like a neuron, right? So I can at will I can create, I know the recipe to create periodic spikes, I know the recipe to create aperiodic spikes. Now I have to put it in a circuit and do computation, which is what we are doing now. I am not going into details of that, okay? Now also just to cut down the, because my time is almost up, so if I measure, so this is the electrical signal, and simultaneously if I measure the mechanical signal, because I said these are also sound waves, right? So simultaneously if I measure the mechanical signal, this vanadium dioxide also expands and contracts, right? So it's, if I'm oscillating just the device part, mechanically also it's oscillating, right? It also turns out that it's not just mechanical oscillation, but even because it's a phase transition, the refractive index also changes, right? So of vanadium dioxide. So it's not just electromechanical, but it's also electro-optomechanical response, right? So everything is coupled to each other, and then so the details then are what comes first. Is it optics? Is it electronics? Is it mechanics? What are the phase differences? All these things are details, okay? Now, if I actually look at what is called the Pockel's coefficient. Pockel's coefficient is very important. I'll tell you what. So it is, if I apply an electric field, the material should change its refractive index. Not every material will do that, right? Only certain materials which have non-centrosymmetry or whatever, they can change their refractive index when I apply an electric field, okay? So if I look at the Pockel's coefficient of this sort of an oscillation, because refractive index is changing, I'm applying an electric field oscillation with that refractive index is changing, that's huge, right? So that's about 20 nanometer per volt. Whereas the best Pockel's material has a refractive index, has a Pockel's coefficient of 1 nanometer per volt, right? So it's quite different, correct? Now, if you go back to the previous talk where Shankar had said, so this is my optical computer from Xanadu, quantum computer, right? So I have these sources of qubits which are all squeezed photons. This is a photo detector. Let me not care about the source or detector because Shankar had already explained. But he said that, okay, I have all these paths, but in these paths I need what are called phase shifters. I need this phi, 2 phi, the thing, if you remember his diagram, right? Now what are these materials that can phase shift light? They are materials, so I need some phase shifting in some gigahertz frequency, let's say, right? Then I have to apply an electric field which is in gigahertz, frequency or megahertz frequency, whatever frequency you consider. And this material should change its refractive index. If it is changing its refractive index, it is changing the phase of the wave that is propagating underneath as a waveguide, right? So what is the material that is required there? It is these phase shifters or these materials that can change refractive index with light. One of them being vanadium dioxide, which has a huge refractive index, but the losses are large, so you have to compensate for that. And the other one that we are also working on is what is called barium titanate along with Shankar, which also has lossless but less Pockel's coefficient. So Pockel's coefficient is important in that fashion. Okay, so eventually, so even the electromechanical coefficient is large, so you can use these, even if I don't care about quantum or neuromorphic computing, I can just use this as what is called a piezoelectric device, right? So I apply, electric field and I can, so I'm a material scientist, right? The end application I can, if you want it for quantum, I'll give it for you for quantum. If you want it for neuromorphic, I'll give it for, if you want just a piezoelectric device, I'll give it to you, right? So it's a phase transition. Phase transition is like the BAP of everything. You want any property to change, everything will change during the phase transition, okay? Now, finally, I would like to end by showing this. So I said there should be a sound wave that is propagating essentially, right? So we make these nanowires of vanadium dioxide and we try to excite this part, right? So this part is excited. There is both a mechanical oscillation as well as an electrical oscillation that happens in this part. We want to see if the mechanical oscillation is actually propagating, right? So we want to actually measure and see that if there is a real sound wave or is it just an oscillation confined between the, so in the cell membrane, right? So it is not propagating through the axon, but it's just in the cell membrane, right? Is it a sound wave or just an oscillation, right? So that is the question that we ask, and these are very recent results where, So first of all, this device, when it is excited here, it has both sound wave, this is the mechanical signal, this is the electrical signal, both of them sort of coincide with respect to each other. But if I'm measuring it here, right, so here also I have this mechanical signal that is coming up. This is the electrical signal that is measured here, and simultaneously I'm measuring the mechanical signal that is measured here with a slight phase difference, right. So this is something that we are trying to understand now, but it looks like indeed this is some sort of a sound propagation that is happening in this nanowire geometry, right. So this actually is like a neuron. This is your cell membrane or your soma or whatever where the action potential is generated, and this is where the action potential propagates, right. Now how do we reduce the losses, etc., right. So in this nanowire geometry we are trying to look at that. Okay, so with that let me conclude. By saying that, okay, so materials, so in general are very important ingredients, especially for quantum computing, for neuromorphic computing, all these aspects. Now, if I take something called a quantum material, I don't need to, look for application which is only in quantum computing, right? So here I'm showing you that quantum materials actually fire like neurons, right? So their application is in neuromorphic computing, one of the applications. The other application, so I also said that you can use them as modulators or phase shifters. That goes into an all optical computer, right? And so on and so forth. So with that, let me conclude by thanking all these people who are doing all this work in my group. The facilities that we have in ISC that we can use to do this work. Now, for all the students here, these facilities, so I encourage you to come here as interns or, so use some opportunity to come here and then, get yourself used to such niche measurements and niche facilities if there's an opportunity. Okay, so with that, thank you very much. I'll take questions. All right, so it is very clear or very unclear. So, yeah, she has a question.
Good morning, sir.
Yeah, good morning.
I just had a very small...
What's your name?
I'm Samhita.
Samhita, tell me.
So, a very small question. In the vanadium dioxide diagram, there was sapphire, right? It just came into my mind. It was bugging me all the way through the presentation. Why is that sapphire used there?
Why is sapphire used? Okay, good question. So I said I want to grow single crystals of vanadium dioxide, right? Single crystals of vanadium dioxide don't grow very well on silicon. Rather, you should use sapphire because sapphire provides a good template, crystallographic template for vanadium dioxide to follow, right? So that's the only reason. Eventually, you want to transfer it onto silicon, whatever you are doing, because all my motivation was, okay, we have to put them on silicon, right? So sapphire will not cut, right? So if I'm doing it on CMOS, but that's a very good observation. Same thing, if you look at the other material, I was using something else called, I think, lanthanum aluminate, right? So I showed that there's another material called iodinium nickelate, and I was growing it on a substrate which is not silicon, right? But right now, I think we are also trying to grow it on silicon, and so
thank you, sir.
Get the similar properties. On silicon, there is some property compromise that you get, right? So.
Yeah. You said negative differential resistance would lead to an oscillator.
You can build oscillators.
Yeah, we can build an oscillator. So, if there is a negative differential capacitor, capacitance rather, can we exploit it?
Yeah.
Something else?
Sure. You can exactly do the same things with an ND in the negative differential capacitance. Although people use it for reducing the sub-threshold, switching on a transistor. So they go below 60 millivolt per decade and things like that. So you can use it to build an oscillator. My only issue with all the literature, okay, maybe I should not say things, my opinions, but so my only issue with all the literature on negative differential capacitance is, to me it is not yet clear that what they are seeing is negative differential capacitance, right? If there is some resistive element or an inductive element there, I am not sure if they are taking care of that. Right, so that's so it can eventually just be an LC oscillator or whatever, right? So which they are trying to interpret it as some negative differential capacitance, but that is the literature that I read. So I don't work on NDC, but yeah.
Yes, sir. Is it the same way that safe memory alloy is nitinol?
Sorry,
nitinol, safe memory alloy.
Nitinol. Yeah. So shape memory alloy. So the way I remember it is, you heat it and there is, so both with stressing and heating, you have a phase transition.
Yeah,
that is true.
Yeah.
You're right. So it's a phase transition.
Yeah.
That's a structural material though. You use it in aerospace, but you don't use it for electronic applications, because even if you heat and even if there is a phase transition, both states are metallic. I don't get this contrast, right? So, and if it is metallic and I'm sending in a lot of current, I also have a lot of losses. So I want to have, one state metallic, fine, I'll live with it, but the other state should be my ground state, which is insulating, where it doesn't conduct a lot of current and the power consumption is less, right? So that's why I don't use completely things that are metallic in nature. But nitinol, it's a shape memory alloy. People use it in aerospace industry and other things. Similar phenomenon in the sense that you can induce phase transitions by stress, you can induce phase transitions. Fundamentally, if you look at it, all these are what are called martensitic phase transitions in metallurgy, right? So, yeah. Yes. What's your name? Shriya, tell me. Yeah, I can hear you.
I just wanted to ask, sir, are there set defined elements that you work upon which show this Mott transition, or is it experimental based?
I mean, okay, that's a good question. There are materials known to show Mott transition, right? That is one thing. So we take from that database, right? So materials that show Mott transition. But recently, what we have been seeing is something like titanium oxide. So I said titanium oxide has a 4+ oxidation state, right? If I reduce it a bit, then I am filling the D states, right? That also shows a Mott transition. Right? So recently we have been exploring these sort of things where, I mean, I think if you read literature from 60s and 70s, some Russian would have said it already, right? But it has all gone, into some sort of, no one has reported them again and things like that, right? So because it's from Russia. But these things are known in literature, but, so we are trying to unearth them again. So there is no new discovery of a Mott material from our group, let's put it that way. Okay, so I said titanium oxide can be Mott transition if I reduce it a bit, and then we looked at literature, it's already there in 60s or 70s. Someone said that that's possible, and they have also experimentally measured it, right? So that's.
Thank you, sir. Thank you so much.
So thank you for the audience for the good questions, and thank you, Professor Nukala, for
Thanks, Saman.
And I would like to present a token of appreciation on behalf of QRP for the nice.
Is there a photo? Okay. All right. Thank you. Thank you very much.